It's my pleasure to welcome Luke Oeding again to give his second talk on representations of coordinate rings. Yeah.
Great. And I will share my screen. This works again. Great. Okay. So this picture. Okay. We're going to come back to that picture. So thanks again for invitation to give these lectures. I'm really happy to participate in this program. So we were talking about coordinate rings and GL representations. So I want to emphasize one of the sort of reemphasize the goal is to find all equations for X inside of some PV for low degree. That's all we can hope for now. We haven't talked about any methods for saying that these equations we're going to find are enough, but I want to say this about all because there are lots and lots of methods for constructing invariants that seem sort of ad hoc, and some of those are much better than what I'm talking about now from the point of view of being able to compute equations in higher degrees. But the advantage of this approach is that you know that you have all the equations in that degree and lower once you're done. Okay, you don't know anything about higher degree, but anyway, sometimes this is sufficient because you have varieties that are have their ideals generated in low degree, and you might be able to find all of those equations there. And we want to describe them in terms of representations. In terms of representations, because if two people give you a set of equations, well, they may not be given in the same basis. And so how do you know that you have the exact same equations? Well, if you give the G module description for whatever your group G is, then the G module description is invariant. The description in a basis or so on could be completely different. There's not, a preferred basis necessarily. There's one that I would pick that seems canonical to me. But anyway, this allows you to compare. So that's the sort of approach. And like I said, I'm not saying that we can find the highest degree equations or the best equations, but we're saying we find all the equations in low degree in terms of representations. And there are many, many other methods for finding equations, which can be very useful still, which would be the subject of a different lecture series. So, and so we were at the point where we said, okay, so we know the set of irreducible representations for GL of V. These are these Schur modules S pi V tensored with a twist. And I'm going to write this as S pi V of minus T. And for this lecture, it's not super important to deal with these twists because we have degree floating around that allows us to figure out what the twist should be for every representation. So the Schur module, this is the SLV module, and this is an extra, this is SL of V across a single one-dimensional torus, and one-dimensional torus has, is abelian, and it has one-dimensional representations, and that's how I'm going to write those. So anyway, those are the irreducible representations of GLV. And we have the irreducible reps for S symmetric group, SD are pi partitions of D. So, and you get the representation, which we just called bracket pi. And then we had Young symmetrizers, which are operators V tensor to the D to V tensor to the D, and their image, this is say C pi, the image of C pi is S pi of V, a copy of S pi of V. So the operators themselves are come from this representation. You have a basis of the symmetric group representation given by standard Young tableau, and then the image of that operator gives you a GLV or an SLV representation. And you can take a basis to be the standard semi-standard tableau of shape pi and content 0 to n, if you like. Okay, so those are some of the things we talked about. And this description came from Schur-Weil duality. Okay, so I want to give now, go back for a second. So we were talked about the Chow varieties. Yes, okay, good. So now we want to talk about the case of G equals GL of V1 cross many copies of GL of V D. And we want to understand its representations. This acts on V tensor to the D, which we're going to call, we could label each copy of this V sub D. For now, I'm going to make all of my vector spaces the same. You could do this slightly differently where each one is different, but this is going to be, we can think about this as this. In my notes, I think I write this as V vector. So a tensor product of vector spaces. And then we have, well, a product of groups acting on a tensor product. And so it turns out that the irreps of G are just these multi-partition functors and up to a twist, which I don't care so much for this lecture. This is going to be S pi 1 V 1 tensor. Okay, all of these. So the notation I'm trying to find, use shorthand when possible. So a multi-partition pi vector is pi 1 to pi d, where each of these pi I is a partition of some other letter, say E. Okay, so we take and the irreducible representations don't have to match the degree. So this is just some integer. What we really care about, though, for the purpose of this lecture, is we're interested in the coordinate ring where these varieties and spaces of tensors live. So this will be C V vector, which is, okay, graded by degree. I'm using D and E a little bit differently. Okay, so E greater than or equal to 0, S E of V vector. Okay, so this is the coordinate ring. It doesn't look like I've done much, but now I need to understand this module as a G module. So there's a proposition, I learned of it from Landsberg and Manivel a long time ago, but it follows from Schur-Weil duality that sim E of V vector is a big direct sum over these multi-partitions. Now, the multi-partition is going to be a partition, a D-tuple of partitions of the same number E. So then S pi V vector, and often it's written like this. Okay, so far I haven't really said much because everything is hidden in this multiplicity n sub pi. But these multiplicities can be computed by characters, n sub pi, multiplicity. But I prefer to think about this as a direct sum over pi, multi-partition E, the same part here, these things. And then I want a tensor product with a module, a module for a product of symmetric groups as pi. So M sub pi is just abstractly a vector space of dimension n pi, but I want to emphasize that if you can form a basis of this vector space, then you actually can do computations with it. So if I want to understand that this is, could be thought of as the multiplicity space or the highest weight space, depending on which vector you take from the other module. multiplicity space. Okay. This proposition, I want to kind of prove it because the proof shows you how to do the computations. Okay, so anyway, before I prove it, so once I'm interested in finding all the equations of some variety, so I need to be able to parameterize all the irreducible representations in the coordinate ring. Grading by degree gives me this, grading by G gives me this, as long as I can compute one of these multiplicity spaces. So let's see how this works. So the first thing I can do though is V vector tensored E times. This contains sim E of V vector, right? Certainly the symmetric tensors live inside the tensor algebra. So, but on the other hand, this V vector tensor to the E, it's kind of in the wrong order. It's V1 tensored to VD, tensored with V1 tensor up to V sub D, It's times the same thing, V1 tensor up to V sub D. Okay, but it's because tensor product on the level of vector spaces is commutative, I can rearrange everything and I'm going to write equal, though I should probably write isomorphic. This is V1 tensor E times, tensored V2 tensor E times, tensored with VD tensored E times. Now I can use my statement of Scherweil duality that allows me to compute each one of these. Remember that V tensor to the E is the direct sum of representations of the symmetric group pi, a partition of E now, tensored with S pi of V with no vector. That's just a single partition. So this is the Scherweil duality statement essentially. And so I can apply this in each case, right? I'll apply it here and et cetera, all of them. So this guy is isomorphic to a big direct sum now over these multi-partitions, all of the same integer E, S pi 1 V1 tensored S pi D VD tensored with okay, I'll move this over. Maybe. Tensored with the pi 1 tensored with pi sub D, this representation. And this is going to be, we'll call this M sub pi vector tilde. We're not quite there yet. In order to, this is in the wrong vector space, right? And we have to project to the symmetric part of this tensor product. And so after we do that, we get the result. So take SD invariance here, and we get the result. But I could take it, I could say something, say this in a slightly different way. I could project onto the symmetric part. And that would do the same thing. So what I can do is I have a basis of a tensor product. You know, I could think about these as their own vector spaces, and they each have a basis of standard tableau. And so then the tensor product of a couple vector, several vector spaces has basis given by the tensor products of the basis elements. And so now I have a basis of this space, and I can then project the elements of that basis to get the map that gives the projection of the whole space into the space I'm looking at. So linear algebra 101, if you want to understand a linear map, apply it to a basis and write its result. You write the results in terms of the basis of the target. That gives you the matrix representation of the linear map. And that's essentially what we're going to do here to compute this. And I think at this point, I want to switch to an example just so that you can see how this is going to work. So that's it for the proof of that proposition. Is it your question?
So you are giving a computational way of actually getting these SD invariants from the tensor product of
Yes.
things, and you're saying given that this there is a good basis in SPI, there must be a nice way of writing up this projection matrix.
That's right. Yes. Yep. And this is where I'm actually going to do interpolation when it's time to do interpolation.
Okay.
So I'll first describe how to write down all these polynomials, but then we're going to describe how to actually just evaluate them instead of writing them down, which, just like the determinant, is much easier to evaluate on a matrix than it is to write down the determinant. That will be the case for these things.
Okay. Nice.
Just arranging my notes here. So let's do this in an example. And I hope that you'll be able to infer the general case from this example. So let's do an example of degree 4 for binary invariant for C2 tensor, C2 tensor, C2. Okay, so there is an invariant, it turns out. It's one dimensional. So we're looking at, C2 tensor, C2 tensor, C2, and the coordinate ring C sub 4. And then it turns out there is a one-dimensional space of invariance here for GL2 cross 4 or cross 3 is our group. Okay, so the first step is to note that the tableau, the standard tableau of shape 2, are the ones that we're going to need for computing something that's going to be invariant. If you go through the dimension formula, to get invariant, you have to have a box that has the same height as the dimension of the vector space that you care about. So these guys, there's 2 of these, so 1, 2, 3, 4 like this, and 1, 2, 3, 4 like this. Those are the 2 standard tableau of that shape. So they form a basis of the representation of S4 like this. So basis.
Mm-hmm.
Then I need to compute. I'm interested in this Schur-functor S22 of C2, and I have 2 ways to write down elements from this. I have 2 copies of this thing, tensored with 2, right? This is what occurs in the Schur-Weil duality statement. So this thing is 2-dimensional. I'm just going to do one of them to see what happens for this case. So I'll get a copy of S22 C2 from using the C, let's call this one T1, CT1, says take V1. Now I'm labeling my vector spaces again. Hopefully it's not too confusing from, let me do this because there's going to be too many labels. So we'll call this A, B, and C. Okay, so we'll have A1. This is just C T1 on A tensor to the 4th to A tensor to the 4th. Okay, and so then the Young symmetrizer algorithm says skew symmetrize the first 2. So I'll call this wedge 2 of A12. The first 2 vector spaces get skew symmetrized, and the wedge 2 of A34, the second 2 get skew symmetrized. Then I map this back into A tensor to the 4th, and then I map it to sim 2 of A, now the rows 1 and 3 tensored with sim 2 of the rows 2 and 4. Okay, so the lower indices tell me which vector spaces am I really symmetrizing or skew symmetrizing, and then I map this back to A tensor to the 4th. So that's what this Young symmetrizer does, just for one factor. Okay, but I need to do this on all factors, and so now let me show this picture. So this is the picture now. I can't draw on this screen as well as the other one, but this sort of shows what I'm doing in terms of wiring diagrams. So I skew symmetrize, in blue here, the first two strands or the first two vector spaces, and then the third and fourth, and then I have to weave them around. And when in black, the black wires produce the image of the first Young symmetrizer, but I have to do this 3 times. And so I just kind of copy that. It turns out to get something non-zero, I have to pick 2 of the same and 1 different of the tableau. So this is T1, T1, and then T2.
Oh.
And in order, everything's all A's in black, and then all B's in orange, and then all C's in red. But I need something that goes ABC, 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 not A, B, 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 C, 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 right? So I have to take something from each of them and put them together, and that's what I'm putting in green here.
Okay.
So let me come back to my drawing. So I have, S22A tensored S22B tensored S22C. This is in A tensor the fourth, tensored with B tensor the fourth, tensored with C tensor the fourth. But I really want to project this into Sim 4 of A tensor B tensor C. So I have to reorder everything. Okay, so let's just write down quickly what the result of this initial, just this part was. This is all spelled out even more carefully in the notes, but just for the discussion, this is B T1 from before. So B T1, I can feed it A1 tensor, A2 tensor, A3 tensor, A4. Just if I tell you what it does to a basis, then you know what it does to everything. So here's a basis vector in A tensor to the fourth. And what it does is it writes, I'm going to add an extra index to each one of these, and it's going to be the determinant of A11, A22, A1. Let's see if I make sure I do this in the right order. Yeah. So these guys, this is, yeah. This determinant times this other determinant, A31, A32, A42. Okay, so this is what I'm writing as A1 wedge A2, is this thing, and then A3 wedge A4, I'm writing as this, but I'm keeping track of which vector space every vector came from. And by keeping track of everything with indices, symmetric products and skew symmetric products and tensor products essentially all end up being the same thing, because I have the indices to tell me where I am in the order of multiplying things. So I multiply all of this out, and I get, the product of 2 determinants. I get 4 terms, and they look like this: A1, 2, A2, 1, A3, 2, A4, 1 minus A1, 1, A2, 2, A3, 2, A4, 1. Minus A1, 2, A2, 1, A3, 1, A4, 2, and then one more, A1, 1, A2, 2, A3, 1, A4, 2. Okay, so 2 minus signs, 2 plus signs. Okay, so this guy is an element of, this is in wedge 2, A1, 2 tensor wedge 2, A3, 4. Okay, so that, and notice that every term has a 1. In the first index, there's a 1, a 2, a 3, and a 4 in every term. So the first index has 1 of each of the numbers 1 through 4, and then the second index can be anything it wants. Okay, so then I do the same thing for I'm going to skip the symmetrization because of this, what I'm mentioning about the indices. I could put a circle here, I could put a tensor product, I could put any type of product I want. If all the indices are different, then those essentially are the same thing. And that's useful computationally, because then you don't have to program what a tensor product is or a symmetric product in your language. Okay, so then I do that, and so when I do this BT1 on the A's, and then it turns out I can do BT1 on the B's, tensored or times C BT2 on the C's, like I did in the picture, I get a product of determinants that look like, you know, this determinant times this other determinant with that, which have A's in them, and then another determinant with B's in them with indices times another determinant with C's times another determinant with C's. So now you can count how many terms you're going to get in this expression. So you have 2 for each 2 by 2 determinant, and you have 6 of them. So you're going to have 2 to the 6 terms, and I don't really want to write all those out because our time here is short. But here's a term. This is going to be A21, A32, A41, B21, B3. Oh, I skipped. Hold on. Working with multiple. Okay, so like I said, we had all these things that are like A1, 1, A2, 2, A3, 1, A4, 1, something like this, times something else in B's, etc. And we said we have 1 of each of these terms. So here's the step I think is perhaps a little bit confusing. I'm going to replace, and this is all quite algorithmic, replace A1I, B1J, C1K with a tensor variable Xij, So this is in A tensor, B tensor C, whereas the other ones were in products and there are extra indices keeping track of which copy of A and which copy of B and which copy of C you took everything from. So every time I see an A1 something, a B1 something, a C1 something, I'll replace it with a single variable like this. And I can do this with the coefficient command, or I can do this with the differentiation, but you have to pay attention to coefficients. Your calculus student should be able to do this sort of contraction. And so what you get then is something that's going to have an X. I guess I had an A11, so I'll have an X1 for the A11. And then maybe something else. Suppose this one was B12, then I would put a 2 here. And suppose the next one was C11, then I would have a 1 here as the first coefficient times whatever else was left over. And in this case, it would be A22, A31, A41, B something else, and C something else. We have many other terms. In this case, I think I still have 64 terms. But now some of the A's or B's and C's have been replaced with X's. And then I do this again. Replace A2I, B2J, C2K with Xijk again. And I'll get something that has X2 like this times X something else. So 2, 1, 1, whatever, times A's, B's, and C's. And then I keep going. I do this 4 times, and eventually I get this, finally I'll get something that looks like this. 1, 2, 2 squared, X2, 1, 1 squared, minus 2, X1, 2, 1, X1, 2, 2, 2. There's many, many terms, and it's kind of silly to write them all on the screen, but plus there's 12 terms here.
Correct.
And this is the Cayley hyperdeterminant.
Okay.
Which is not the usual way you construct Cayley's hyperdeterminant. There's an ad hoc method called Schlafly's method that computes the same invariant, but you can compare. It's nice to know another way to compute the invariant, because then you can check whether you got the right answer. And was it really okay to not write a symmetric product and just treat everything as a tensor product with extra labels and so on? Anyway, there's one additional thing that's really nice about this. Okay, so if you use a program like Maple keeps parenthesized expressions together, whereas a program like Macaulay 2 does not. Macaulay 2, it automatically just expands every product. it's possible that doing this without expanding the products is faster. And I've seen that many times in Maple versus Macaulay too. So you have to pay attention to which language you use to implement this. But also you can convert this algorithm into an evaluation algorithm as well, because as soon as I have something here, if I want to evaluate this at a point, I can plug in. So if I plug in a point at this stage, I can also plug in, to this one here. For every time I see one of those variables, I might as well put the coordinates of the point that I want to evaluate at. And so these 64 terms will now be 64 terms with some numbers in front of them instead of a bunch of variables. And it's possible that you get some cancellations that occur early in this process, and you might be able to evaluate very quickly. In fact, because of this number of terms explosion, the evaluation happens in the order of fractions of a second, whereas producing the invariant probably takes minutes, hours, depending on how big of a form that you get. So one of the things you can do is, even if you didn't know the character theory that would tell you, or the shuffling laws that would tell you whether or not you got a zero invariant, we have this multi-tableau, 1, 2, 3, 4, tensor 1, 3. Okay, so if you did this one, it turns out that this is going to project to 0. If you do the other one, these are the only options after relabeling of triples of tableau of this shape. Okay, so this one projects to the hyperdeterminant when you do this process. So character theory will tell you that there is a one-dimensional space of invariance here. We had two different options of same, or same, different in terms of the tableau. I'm saying it that way because I could apply an action of S4 and relabel everything, and none of this picture changes. You don't actually have to start with standard tableau in this picture to do anything that I said. You could take any tableau. What if you didn't know the dimension of the space of invariance? Well, then you could take all triples of tableau and try to do interpolation on this space by plugging in different points where these invariants don't vanish, and find, again, this is something we do in linear algebra. If you want to tell if two functions are independent, plug in two different points and form the 2x2 matrix of values of that function, of the two functions, f of x1, f of x2, g of x1, g of x2. And if this determinant is not 0, then f and g are independent. If the determinant is 0, you don't know anything, right? Mm-hmm. But you can find independence by evaluations. So so here's a method for computing a basis of m sub pi vector, and hence the I always mix these up, the Koska numbers and the Littlewood-Richardson numbers, but I think these are the Koska numbers. You get a basis for this space, and it might not be the most efficient way to compute it. Like I said, there's character theory computations you can do instead. But if I have a basis, I can actually do something with the space. So a method for computing a basis of this is going to be, take points, say xi, in a tensor B, or in V vector, sufficiently generic, so random, and take these tableau tuples, say T. So it's a tensor product of tableaus, and then evaluate, T of X, I, so call this J, T, J, X, I, and keep doing this until you get, well, you don't know when to stop if you don't do the character theory. So until you have enough independent vectors, independent T sub J's, tableaus. Okay, and this is the multiplicity space for the coordinate ring. Once you have a basis of that space, you can do the exact same thing for computing the intersection with the ideal of the variety that you care about. So if you want the ideal of X inside of, in degree E, inside of C V vector E, then you evaluate, you choose your points, Xi in X now. And if they're sufficiently general, random, then you can compute the kernel now. Suppose all these T's are independent, and compute the kernel of this T sub J X I matrix. Okay. And that will give you a basis of the of what I'll call M sub pi intersect with ideal of X.
Okay. And here,
that can be,
when to stop, you just pick up enough and just see where the dimension sort of stabilizes, is it?
If you didn't do the character theory calculation here, you could do all the tuples that span a basis of the tensor product space. And we're projecting into the symmetric product space. And so we could overdo it, right? I mean, we have way more, we know the multiplicities in the tensor product space is just the product of all these Schur modules, right? So we just take if you took all the tuples of standard tableau in each factor, then you would find a basis, but you could stop once you get to the dimension given to you by the character theory.
Okay.
And that's much more efficient. But if you didn't know the character theory, this would tell you the answer also. And you can also do these kind of things I was saying, like same, different. You know that you're symmetrizing over the symmetric group. And so renaming things are going to give me the same results. And so, the only chance I could have here really is if these two are independent or dependent. And one of them happens to be 0. So, but what we don't know is if, if I put this different tableau in different spots, if I get something different, and that I have to check. It turns out that I get the same up to scale, I get the same polynomial every time, which is not guaranteed. In fact, many times that's not going to be the case. So this is a method for computing a basis of this space. One other thing I find quite interesting is there's a graphical version of this. And so anytime you can do some of these computations in a way that saves time, maybe we would love to be able to do this without the computer. Okay. Right now, what I've described to you really needs to be done on a computer because you have 64 terms, even in this small case. You don't want to fill pages and pages of notes, but is there a way to evaluate these things without using the computer? And if we could do that, then we would actually be able to prove something for larger varieties, families of varieties, and so on. And there's one example that I worked on with Claudiu Raicu, and we were able to do this for the tangential variety of the Segre product. And Claudiu also did the same type of thing for the secant variety of the of the Segre product. Let me jump to, because Pascal had asked about the Chow variety, I want to talk about SLV modules in C of SIMD of V. Okay, so the way I've set things up, it allows me to do this, and I won't have time for this, but I could also do the case of wedge D of V. Just everything I'm going to say for this case, you could just transpose. Just sort of turn your head sideways and you'll get the other example. And so this is where, this is where the ideal of the Chow variety lives, for example. So if you could compute the irreducible representations inside of this coordinate ring, then you'd be able to check whether you have the equations or some of the equations of Chow varieties, and this is where the permanent determinant orbits live, and so on. So this is interesting to us. So I'm going to use, you could use something called tabloids and see Raikou 2012 or Oeding and Raikou a bit later. I find labeled tableau a little bit easier to describe, so I'm going to do it this way. So I'm going to do this with an example. So the one trick is that we already looked at SIMD lives inside of V tensor to the D. So I have a projection from the space of representations for C V tensor to the D. I can map this down to C of SIMDV like this, right? So if I could just compute this symmetrization, then maybe that's sufficient to compute all of the representations. But one of the things that I have to compute, though, I'm interested in SIMD of SIME of SIMD of V. These are the sort of the pieces. This is the degree E piece of this, right? And I want to decompose this as a representation of just one copy of SLV or GLV. Over here, I'm sort of implying that I have D copies of SLV, but they act diagonally. I want to look at the diagonal action of one copy inside of the product of all of those copies of GLV. So labeling all the vector spaces, giving them our arbitrary labels, even though they're all exactly the same vector space in this case, is still useful. So let's do this for the degree 4 invariant for binary form. So we're going to do binary cubics. And I'll compute the discriminant. Okay, so I'll give you an equation that you can check. You already know what the discriminant of a binary cubic looks like, but here's the tableau description. So I'll take this tableau, and now instead of taking tensor products of tableau, I'm going to write, here's a tableau that I would get if I just smashed together all of the tableau in the previous case and remove the tensor product symbols and just put everything next to itself. This doesn't look very standard. It doesn't look very much like a standard tableau. But this is a tableau that has the property, if you can read my handwriting, that it has 3 A's, which I've labeled A1, A2, A3. The labels are a little bit superfluous, but they're necessary for the algorithm. 3 B's, 3 C's, and 3 D's. This is going to give me a Young symmetrizer, but I prefer, this is not standard. And it's not going to be D standard either. D for the number of factors in our case is 3. But you could shuffle the columns around. It turns out you could produce this one instead. And I'm going to stop writing all of the barriers. I'll just write the content. A1, B1, A2, B2, A3, C3, B3, D1, C1, C2, D2, D3. Okay, so this tableau has content A1, A2, A3, dot, 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 B1, dot, 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 C1, dot, 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 D1, dot, dot, dot. Okay, so I have content as before. I just had content A, B, C, D, or 0, 1, 2, 3, 4. Now I have content with extra letters. And if I use different letters, I can save one subscript, which makes it a little bit easier to write things. Now I'm going to do the same thing that I did before. I'm going to take each column. Each column is corresponding to a determinant. So the column A1, B1, I'll produce A1 wedge B1. This is the first step of the skew symmetrization of the Young symmetrizer algorithm. And this is just the determinant A1. The rows are A1 and B1. Okay, and I do that for every column. So then this column will be A2 wedge B2, and I'll put in the rows A2 and B2, etc. The last one, C2 D3.
Sorry, how did you come to that? From the first one, how did you get to this one? The one with tilde in the
Okay,
front?
so one thing that I've left out of this lecture series is shuffling rules, but
Okay.
I'm allowed to change in the
Okay.
version of shuffling that I'm allowing for this discussion is I'm allowed to change the order of the columns as long as they have the same height.
Mm-hmm.
All of these columns have the same height, and so I've just it's not quite, it's a little bit of a lie, right? Because I have C1 over D1 to begin with, and then C1 is over D2 here. But I'm also allowed to, a different version of the shuffling is I'm allowed to reorder everything in the same row for free.
Okay.
So depending on which shuffling laws you use, you can shuffle the tableau. But it turns out as far as like this method for computing a basis, since I'm not computing characters and so on, I actually don't care about the standard part for the purpose of the algorithm. But if I want to try to compute the character using the algorithm, maybe I want to only use standard Tableau, and that'll save me some time. But if I'm going to just choose random fillings, the thing that I need, D is three in this case. So I need 3 of each letter.
Correct. Okay, so long as it's the same tabloid, you're saying you're sort of fine, is it?
Yeah.
Okay.
And then the other thing I can do automatically is I can't have any repeated letters in the same column.
In the same column, correct.
Because I'm going to skew symmetrize something that's already symmetric. And so that's something I'm not allowed. All right, so I do this product of, again, 6 2x2 determinants. And there's just a slight change now. I multiply all these together, and now I'm going to replace, it'll be A1, I, A2, J, A3, K with X. And now there's one other thing, sort IJK. Because I want symmetric tensors, their indices need to be symmetric. I'm going to choose the sorted order to be my tensor variable. So this is in Sim3 of C2. And then I'll do that same thing, but now with the letter B, B1, I, B2, J, B3, K with the same thing. And then C1, I, C2, J, C3, K, and then D1, I, D2, J, D3, K, do the same thing. Again, I could evaluate at a given point, every time I plug in a variable for the ambient tensor space, I could plug in a coordinate, or I could try to find the polynomial. If I find the polynomial, I end up with this one, 3x1. I get rid of superfluous coefficients also. You can divide by a global constant if you like. Etc. And then, maybe you've seen this before, is 3s1 squared s2 squared minus 4s0 s3 s2 cubed minus 4s1. If I just count the number of 2's. Okay, so this is the discriminant of the sum of si x to the I. That's the discriminant, and this sort of symbolic method, it goes back to Rhoda's symbolic method. This has been around a long time. I'm not saying anything brand new. There are many speed ups and efficiencies that you could do to do this, but this gives you a method for computing invariants or any of the covariants as well. And actually you can compute all of them because you can compute a basis of these representations. Okay, so now I want to describe something that I think could be also useful, which is another view on this is pairing tableau and points or normal forms. So what could we do without a computer? And the notes for this are typed, but they're not on the website yet, so they'll come shortly after the lecture. So suppose I take something. Here's the hyperdeterminant of the in this case we did before, is also known as the Segre product of P1 cross P1 cross P1, and then I take the tangential variety of this. This is the vanishing of the form that we computed earlier. But if we wanted to discover this, this contains points like this: A2 tensor B1 tensor C1 plus A1 tensor B2 tensor C1 plus A1 tensor B1 tensor C2. So A's and A1 and A2 could be taken to be independent, B1, B2 independent, C1, C2 independent inside of, I could think about this as, PA cross PB cross PC, and A, B, and C are all isomorphic to C2. But this is a normal form. And this is also equal to, let's call this little x. This is G times X closure, where I take the A's could be taken as basis vectors, but I have two perspectives on this. I could also think of the A's as being A's, B's, and C's as being parametrized vectors. So I have a parameter space, which is, it turns out, PA cross PB cross PC again, or I could just do A cross B cross C, and I could do two copies of this. And then I can map this into A tensor B tensor C, where I just take A1 and A2 and B1 and B2, just arbitrary pairs of vectors in each C1 and C2 to this form X that depends on A's, B's, and C's. So the orbit description is also a parameterization of this variety, because I can choose any basis of A with the action of GL2. It's two-dimensional. So anyway, for any variety that we're interested in that has a normal form or has a parameterization, we could try to pair that parameterized point or the normal form with the tableau and see what we get, right? And so if we do this, let's just do one factor. Well, let me back up a second. So what is going to be the pairing? Well, the pairing is V with S pi V, a point in the ambient vector space goes to, okay, so I take a point here and I take a Young symmetrizer and I send it to CT of X. That's the pairing. This is not a perfect pairing or anything like that, but I could do something slightly better and describe bipolarization. So this is an aside that's going to be useful. If I have a polynomial, it's homogeneous of degree D, then I can think about it and on V as an element of sim D V star, but these are symmetric D-linear forms. So the evaluation f of x, well, this could go to something we'll call f vector here, is actually equal to f vector, where it eats the same form, the same vector d times. So this is polarization of forms. And you could look at the other polars, but the only one we're going to be concerned with is this. Now, a d tuple of x's, I can think of this as x tensor to the d. This is equivalent information. Whether it satisfies the tensor product, you have to check the multilinearity, but the tensor product is multilinear again. So I have a multilinear form and I can feed it x tensor to the d. So that's what I'm going to do instead. I'm going to take v tensor d times cross sim pi of v, where pi is a partition of d, to c, but I'm only going to describe it on these pure tensor powers, c t pi. And again, this is going to go to c t pi of x, but this is, and turns out to be quite useful. So let's do this example with the hyperdeterminant again. So let's warm up with the Segre. And here's a point on the Segre, A tensor, B tensor, C. Okay. And I would like to pair this A tensor, this is my X for this discussion. Well, X tensor to the fourth is, well, I can reorder everything. So this is A tensor to the fourth, tensor B tensor to the fourth, tensor C tensor to the fourth. And now I want to pair this with this S22, C2. I guess in this case, I just have 3 copies of this. But I also had a basis for this thing. So the basis was for the multiplicity space was given as 1, 2, 3, 4, 1, 3, 2, 4. This is my tableau is this. And so now I have a way to take A tensor to the fourth and 1, 2, 3, 4. This goes to the tableau A, the first A. I could put a number here, but again, these are silly. In this case, I only have one of these A's, so these numbers get erased. And this tableau goes to a determinant, which is obviously 0. So already here, the Segre product, here's something I learned about the Segre product from this pairing between Tableau and forms. I take, sorry, I didn't say this. This is going to be my content. And there's and this is going to be an insertion order given by the Tableau. And then I apply the Young symmetrizer algorithm to the Tableau with the letters coming from the content from the point that I wanted to evaluate at. And so here's the upshot, is that the ideal of the Segre of any number of factors, PV1 cross PV sub D, contains, well, what happened here? I had to take the tensor power of the vector that I started with. So I only get one letter for the content for the first factor, and the same for any of the other factors. So, and that forced me to skew symmetrize something that was the same row in a matrix, right? I had to take the determinant with the repeated row. So those are all going to be 0 unless I only had one row. So and I don't know what happens when I only have one row at this point, but this contains all the S pi vector V vector such that pi vector is a partition of E, at least 2, and pi I has greater than or equal to 2 parts for some I. That's a nice result. The Segre product, we know all of the modules in its in the ideal. With a little bit more work, the only thing that's left out, this is also SD I'll try to write this in the usual SD of V1 tensored with SD V, or this should be an E. So it's the orthogonal complement of this inside of C of V vector sub E. And you can check that the pure powers, tensor product of all the pure powers is non-zero. And in fact, there's a theorem, so an easy proposition for G mod P is X inside of some gamma sub lambda highest weight representation, or in its minimal embedding. This is the module with weight lambda, that the ideal of X is equal to the direct sum over these with an E. You take the orthogonal complement of this sort of weight vector E greater than or equal to 2. And a non-trivial theorem of constant, and you can look in Kumar's book for a proof of this, says that I of X is generated in degree 2. So the whole description that we started with just one factor, you can move this up to any G mod P for G compact semi-simple group, and you can get a similar kind of result for any of these. So that's really, really nice. Just from this observation that you can pair the normal form of the vector with the tableau, and that you'll have repeats in columns if you take something from the Segre or from one of these other G mod P. So let's go back to the tangential variety and see what happens there. So again, we had this A1, A2, B1, C1 plus A1, B2, C1 plus A1, B1, C2. So this is my X now. Okay, and now what is X tensor to the fourth? I'm only showing you this degree 4 example, but the other degrees we should have checked them, and the other modules we should have checked them, but you can see how this would go for these guys. So X tensor to the fourth is going to have terms, different types of terms, right? So the types of terms are A2, B1, C1, just tensor to the fourth, which we already know that what happens there. The weight of this guy is like this. So the labels will be 1 and 2. So the number, and then A, B, and C. So the weight is how many A2s do I have? Well, I have 4 of them, and I have 0 A1s. I have 4 B1s and 0 B2s, and I have 4 of those. Okay, so this is the weight of a term like that. There are more types of terms, and this is the weight. So another type of term I would have would be A2, B1, C1 tensored 3 times, tensored the next one. And then I guess I could do this 2 of each. And then I could do 1 of each of the, 2 of one of them, and okay, so those are the 4 types of terms that can show up in this tensor product of these things. And everything else is the same after relabeling. What about the weight? So over here, the weight is, okay, I have 1 A1 and 3 A2s, and I have 1 B2 and 3 B1s, and then I have 4 C1s. And in this one, what's the weight? So I have 2, 2 for A's. For B's, I also have 2, 2, but for C's, I have 4, 0. And then in this last one, the type is I have 2 of each for A, and then I have, oh no, I have 3, 1 for B, and then I have 3, 1 for C. Okay, and notice that I never get weight 2, 2, 2, 2, 2, 2, which is what would I would need, which was what I need for non-zero on the hyperdeterminant. Let's just see this. I have this tableau. It's 1, 2, 3, 4, and now I'm going to fill it with something. Okay, let's try this weight 3, 1. So I have A 1, 1, 1, A2. So suppose I tried to pair this term with this filling. Well, the reading order says go 1, 2, 3, 4, and I take them in order. So I do A1, and then do the second A1, and do the third A1, and the A2 fourth. And this tableau has a repeat in a column, so it must go to 0. And you notice that any weight 3, 1 or 1, 3 has to go to 0. The only thing that I can't rule out is what if I had one A1, A1, A2, A2, and I paired this with one of these tableaux. Let's just do this one for, it doesn't matter. If I pair with this tableau, then I'm going to get A1, A1, A2, A2, for instance. And so there's a tableau that doesn't have any repeats in columns. It has a chance to be non-zero. We haven't shown that it's not 0, but none of the terms that occur in this expansion have all weight 2, 2. So at least one of the tableau in one of the factors is going to pair with the letters, the content in that factor that's allowed, and give 0. So therefore, here is a one-page computer-free proof that no representation of shape 2, 2, 2, 2, 2, 2 is going to be non-zero on this form. It takes a little bit more work to show that that representation is in fact non-zero. It's not just the 0 module, but this idea could be used to try to describe the ideal, even when the number of terms goes to the tens of millions and trillions. If you had some description like this, there's a few other cases where this is known. So the subspace varieties and things like this, we can do a similar kind of trick if you know about subspace varieties. I'm going to pause for a second because this is a lot of information. See if you have any questions.
Sorry, could you say again what you just showed? It was a lot of double negatives and I kind of lost track of it.
Okay, thanks, Matt. Okay, so I'll write it like this. So here's my S pi vector V in my case is S2, 2. I'm trying to pair a form with this representation, right? This is my example. And so the only weights were things like, 3, 1. Oh, we had this other one where we had 4, 0, 0, 4, 0, 4, something like this, or 3, 1, 3, 1, 0, 4, and so on, things like this. But it's a necessary condition to have a term with a non-zero pairing is weight 2, 2 in every factor. So we have this bilinear pairing, right? We have x tensor to the 4th with S pi of V, and this is equal to, term 1 with S pi of V plus ... plus term last with S pi of V. And what we showed is that every single term in this expansion is 0. So certainly a sum of a bunch of zeros is 0. It's a lot harder if you can't do this kind of an argument. It's possible. There are many situations where some of the terms you can't say if they're 0 or not just from this simple argument. And so it's possible that you have some cancellation when you pair up these terms with the tableau. But in this situation, the bilinear pairing between the normal form and the representation gives you a linear combination of zeros.
Thank you.
Any other questions? Okay, so I found this example to be, and maybe I'll end with this example. So I'm interested in C2 tensor to the 5 for this example. And I still want degree 4 invariance. And so I have these two tableaux, T1, 1, 2, 3, 4, and T2, 1, 2, 3, 4, like this. And so character theory computation could tell you what the space of invariance is. I'm only doing invariance in this case, but you could do other types of representations. But you could just start evaluating T1, tensor T1, tensor T1, tensor T1, tensor T1 on some points, and these are going to be random points. And perhaps you can convince yourself that this is going to be 0 because this, but this is going back to doing the computation on the computer, okay? Then it turns out that if you do all the same, except for one, we'll call this F, sort of the Young symmetrizer associated with all these tableaux. We'll call this F5, and then ... T2, T1, 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 C. Call this F1. ... Okay, so I have a 5-dimensional space. It turns out that these are in the space of invariance. And now I have S5 acts on C2 tensor to the 5. And I want to recall something back in what we taught our graduate students in algebra last year. We have a 5-dimensional space on which S5 acts. So what could the possible representations be? So we only have a couple of choices. So either, and in fact, they're a basis of the space of invariance. So we have a C5 with a S5 action. And so either it's C1, 5 copies, or C4 plus C1. So 5 copies of the trivial representation, or 1 copy of the standard representation and a trivial representation. So I think we often forget that we have this extra copy of S5 acting, and that when I'm looking at a variety that's invariant under the full group, so I have this variety, suppose X is invariant under SL V1 cross SL V5 cross S5. So if that's the situation, if I have a variety invariant under the action of all of these groups, then I can get an even finer decomposition than what we've been talking about before by looking at the S5 modules that act inside of here. So then if it's invariant under the action of this group, once we decide that this is actually the representation of the space of invariance, we can reduce that 5-dimensional computation to a 1-dimensional computation here. And in fact, another 1-dimensional computation for the C4, because that C4 is either in the ideal or not in the ideal. You can't have a subspace, a further subspace of an invariant space, because this is already irreducible. So any representation in the ideal of X is going to be an irreducible G module. So think about what we did. I mean, we're looking at degree 4 C of C2 tensor to the 5th. So these are 32 variables. And then we take the G invariance of this thing, and it turns into 2 1-dimensional computations in degree 4. instead of 31 plus 4 choose 4, which is basically 30 to the 4th power. And I did this just recently for some other variety, and I found that this invariant space of invariance, this module of invariance was in the ideal, which was unknown before. And also we can skip one extra step. I know a basis of this standard representation. A basis here is F5 minus F1, F5 minus F2, F5 minus F3, and F5 minus F4. This is a basis of that space, just from your, back in the first time you ever saw any representations of SD, the standard representation has a basis like that. So I can save even more computation, and this is something I'm a little bit excited about, because I think that we could exploit this for sort of much bigger examples than we were able to compute before, by sort of knowing in advance what the S5 or SD action could be on the space that we're studying. Okay, that was a lot of information. The upshot, as I said in the beginning, this is a method for computing all the equations in low degree, but you may want to look at sort of Young flattenings. You may want to look at hyperdeterminants. There's other ways that you can compute Young flattenings, and there's sort of this other method called border apolarity. There's many other methods that you could try to consider. But again, the advantage that this method has is that you know that you've got everything in low degree. And if you can exploit this sort of partially symbolic, partially computational method for finding invariants, you might be able to do something that you couldn't do on the computer. Okay, I think that's all I have for today. I really appreciate the invitation again, and I'm happy to take other questions, and I will update the notes online later today.
Oh, you are muted, KV, you are muted.
Yeah, no. Yeah, thanks, Luke. Lovely talk, actually. Yeah, I mean, I have also programmed. I rarely do both the actions, actually. Now that you told me, I should really look at it. Yeah, it's usually one of the two that one works with and forgets about the other, as you said. Yeah.
That's right.
Yeah.
Stephen Sam and I wrote a paper in this situation also, where the space of invariance without the S5 action was like 1,000-dimensional, but there's only one skew invariant and only one, or a 4-dimensional space of skew invariance and a 40-dimensional space of invariance for S5. And if we're just looking for an actual invariant, that reduced, this 1,000 by 1,000 matrix to, I guess it was 10 and 39, something like that. Anyway, so a huge reduction on top of something that was already complicated to compute. It turned out to actually allow us to do a computation we didn't think was possible.
Hey, I have a question. So hey, Luke.
Yeah.
So you explained about how you can find equations by in this very specific situation where this large sum is actually 0 on each summand, right?
Mm-hmm.
Where you evaluate the variety and you say, yeah, it's a large sum, but actually exactly it's individually 0. So have you encountered any situation where you can, I mean, with a computer, of course, you can treat more general cases, right? We can just, doesn't have to have that specific structure.
Right.
But is there, are you aware of any case where the structure of the summons is not that simple, but still there's a non-computer proof? So somebody actually analyzed the structure of those types of summons and then could still conclude that the end result is actually 0.
Probably the answer is a little non-committal, yes and no. So like one way would be is if you have one term is the opposite as another term, right? And so if you end up something, the simplest example of which would be like if you had AB on one term and then you had BA on another term, right? And you know the shuffling rule is changing the order in a column you pay by the sign of the permutation. So if you ended up with something like this, then you would get 0, okay? And yes, the work of Claudiu Raicu and then the work that we did together on the secant variety of the Segre product and the tangential variety of the Segre product, actually for all Segre Veroneses, we give a complete description of the minimal generators of the ideal, a complete description of the coordinate ring and all the multiplicities that are there. So using sort of a graphical calculus, which I didn't have time to sort of describe in these lectures, but in a sense, yes, we're describing this pairing. I gave the simplest case, but as you say, like you have to, the tricky part is when things are not 0, right? So what should be the value of one of these? Let me go back up to where I was doing it here. Like, what is the value if all the letters are different, right? So I think what you could do is just, if you see a tabloid or a tableau, you can assign a constant to that number, to that, whatever that constant is. It may be 0 or not 0. And then you could say, well, if I see that constant again, or a multiple of it, then I can start combining things, and you could do that again by hand. One trick is to like try to do a hybrid, I think, where you have the computer doing part of this work. And that's one reason why I use Maple pretty often, because it uses sub-expressions. And so it just names the sub-expression. You may notice this if you ever like output a very long expression with lots of parentheses, that it'll have like %2 is equal to this, and then you'll see %2 several times in the expression, right? And so Maple recognizes those sub-expressions, and if you have a sum of a bunch of things that have the same sub-expressions, it'll combine them, which is the only thing I think is really significantly different, in addition to the other thing I said, where it keeps parentheses together, whereas Macaulay 2 or some other programs will actually expand everything out. Well, if you had a product of many tableaux, you know, let's say even height 3, and you had 10 of them, then you have 6 to the 10th number of terms, but you might still be able to do an evaluation if you don't expand all of those terms out, because you get some cancellations. Or one of the things that was really crucial in this paper on tangential varieties and Segre Veronese varieties is to be able to understand what happens when you peel off some of the letters, but not all of them. Like you stop halfway in this previous description I was saying up here, where you do this replacement. Yep, here. So if you stopped after doing one replacement, you have a tableau together with some X variables. And you could use those expressions by hand and try to say something. Well, how do you know that you didn't do something stupid with the shuffling rules or so on? Like you have to be able to do shuffling with tableau that have missing boxes and so on. And Claudiu really made this did this carefully in a separate paper. So that's a sort of a longer answer to your question, is that if you can handle, you know, maybe you know that once I take out a certain number of boxes, I get a shape that I've already seen before, and I already know that vanishes on my variety. And then so that gives me, I can stop there without doing any more computation.
I see. Thank you.
Any more questions? So
I should probably mention Christian, you know, for everyone else, is one of the experts at this, and you know, they have libraries of filled tableau that, like, once you've already decided that something is non-zero, you can keep this in a library and use it again. Like the hard part of some of this is finding independent tuples of tableau, but once you found some, you could use them again. And the other thing I wanted to say is that all of this, many of these steps can be parallelized very, very quickly. So for instance, these replacement steps, you could send half the terms to one processor and half to another processor and do the replacements in parallel. Or the evaluations, you could evaluate half of your sub expressions on one processor and half on another. And then, you know, however many processors you have, you could separate them. Also, the business of finding independent tableau. Every entry of this matrix can be computed on a different computer. And we did this, the work with Steve and Sam that I mentioned before. This is how we're able to do this. Each box in this computation we had to do in degree 16, I think, took 6 hours. And so we had a 39 by 39 matrix where computing every entry of the matrix takes 6 hours. Well, if you have 39 squared computers, which I do at Auburn, I could do this in 6 hours. Okay. Instead of, yeah.
Nice.
So I like this idea of combining the parallel computations with, and there's a little bit of an art deciding how far down the rabbit hole of trying to parallelize some of these things, because you want cancellations to happen. And if things are happening on different processors, you're not going to get cancellations until the very end of your computation when you put everything back together. But at least doing the interpolation, you can put every computation inside the interpolation matrix on a different computer, and that's super useful for cluster computing. Okay.